Good day and welcome to today's episode. Today we'll be talking about how to identify oxidation number of elements of the periodic table and how to calculate or identify oxidation number of a radical. How to arrive at the oxidation number of a radical. So we start with the first 20 elements where we have 8 groups or 0. The groups are the vertical lines or column we have hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon, potassium, and calcium. Now, basically, we'll be using the first 20 elements of the periodic table to find out how you identify the oxidation number of elements. Now, from group 1, have it at the back of your mind. 8 is the octet state. 8, the octet state. Octet state is a state of stability which every element or atom aims at. So, from group 1, from the knowledge of electronic configuration, group 1 automatically all elements in group 1 has oxidation number of valence number of 1, and then the oxidation number is when the sign is added, plus 1. And you wonder, how is it plus 1? Now, element of group 1 element in their outermost shell has only 1 electron in the outermost shell, needing 8 So this is the only available electron in their valence, that's in their shell, outermost shell. So the valence electron is 1, meaning that there are 7 empty spaces still available for electrons to fill up before octet states can be achieved. Now, you agree with me, it will be difficult to attain 7 electrons or to get 7 electrons. Rather, it is easier to give out this one to somebody or other element that is close to stability. So that is why it is easier for elements of group 1 to easily donate or release their outermost shell electron, thereby making them positively charged. Because as we say, giving is a positive sign. When you give, it is honorable than when you receive. So the positive sign is allotted to group 1 elements because they will easily give out their valence electron, which is just 1. The same principle applies to group 2. Group 2, when you write their electronic configuration, all elements, their atomos or valence electron will be 2. Their valence electron will be 2, having 6 empty space. Why these 2 is just what they have. And you agree with me that 2 is far from 8, which is the state of stability. So 8 is far from 2. Rather, they easily give out these two and donate to become positively charged. Now, the amount of electron given off is the amount of positivity. So if group 2 are giving out 2 electrons, which is the only available in the outermost or valence shell, then they become +2, which automatically becomes their oxidation number. So group 3, the same principle apply. They become +3 because they have 3 electrons only in their outermost shell. So thereby they will also donate 3 because that is still far from 8. 3 is far from 8, which is the octet. So group 3 will be all elements in group 3 we have +3 because they will donate rather than receive. So in this case, we refer to these elements as metals. Because metals will donate, they give out their valence electron to react to it rather than accept. Now, group 4 are referred to as metalloid. Mind you, quickly, I would like to remind us that each group 1 are referred to as alkali metals, group 2 alkali earth metals, group 3 are just metals. Probably in the future discovery will show their own other names. Group 4 are metalloids because they are in the middle of 8. This is half, so they possess both the properties of a metal and a non-metal. So we have ±4. But most often times, carbon, group 4 elements often react as a non-metal because they will accept 4. Now, crossing to group 5. Now, in the group 5 elements, have 5 electrons in the outermost shell. 5 electrons in the outermost shell, giving 3 empty spaces, leaving 3 empty spaces for electron acceptance. Now, 5 is closer to 8, so it will be difficult to give out the 5 electrons at the same time. Rather, they would borrow 3 electrons, which makes them acceptor. So from group 5, we refer to them as non-metals, acceptors of electrons. So group 5 elements will receive or borrow, like I do say, borrow 3 electrons. And when you borrow is a negative sign, it's not a good sign. So they are receivers, which is -3. So the number of electrons they receive is the number of the negativity. So element group 5 elements has -3 oxidation number, -3, because they needed to borrow 3 to be stable. So that leads them to -3. So every element in group 5 we have oxidation number of -3. Group 6 is closer to 8. 2 spaces will be available for bonding or acceptance of electron. So 2 is borrowed or accepted. So that makes the oxidation number -2. And group 7, the halogen family, is -1. Of course, 7 is closer to 8. So 1 will be needed, and it is the group 7 elements will rather borrow or accept 1 electron than give out 7 of its outermost shell electron. So group 8, which is the noble gases, of course, this is the octet state. the octet state, it does not need to give out nor receive. It's already filled up. So the oxidation number here is 0. No valence electron. There is no valence number. There is no oxidation number. It is neutral. Nil. So that is that about identifying oxidation number of elements on the periodic table. So anytime you look out for an element to find out the oxidation number, just check out the group they belong to. The group from group 1 to 3 are metals. They will always donate. So the number of electrons in the outermost shell being donated is automatically the oxidation number, and donating reflects them to be positive. On the other side, from group 5 to 7 are non-metals because they are acceptors of electron, and the number of electrons they accept will reflect to be their oxidation number on the negative side. Talk about group 4 as metalloid and group 8 as noble gases with neutral or no valence oxidation number. Now quickly we are moving to